This is our final set of slides for our first lecture of Circuits 2. We're going to talk about piecewise integration. We're going to use a result from our previous slide that said to integrate over this entire region, we can do so by breaking up the integral limits. And in particular, it said that if you need to integrate between minus infinity and t, any function, f of t, and if we call the result g of t, and to be proper, we should use dummy variables here. Instead of evaluating this, we could instead evaluate this integral, that it's the integral between t naught and t of f of tau d tau plus our answer at g of t naught. We derived that towards the end of the last set of slides, and that's true for all t greater than or equal to t naught. And the importance of that result is that it means we don't need to know our original function of time for all time, including way back at minus infinity. Now we really only need to know what our function is for time greater than t naught. Of course, our answer is only valid for time greater than t naught, but it gives us a way to find that answer. So the easiest way to talk about what piecewise integration is to start off with an example. So here's a function, and we want to evaluate what its integral is. And the problem is that this function is I of t. We don't know what the function is for time less than 0, but we're asked to find out what the voltage is, if the voltage is defined to be the integral of this I of t for any time greater than 0. And we're given the one clue that v at time 0, the answer at time 0 is 2. So the way to solve this is to set up a table. We're going to integrate over different regions, and we're going to figure out what those regions are by noting that they have to have a single formula for I of t. So for this particular problem, our first region is going to be between 0 and 1, because in that region, I of t is equal to 3t squared. And in our next region, between 1 and 3, we can figure out what the value is for I of t in that region. We'll do that in a moment. Next, we'll identify what the start of our time region is. Really simple. Our first number is the beginning of our time region. So for this first example, it's 0. For the next example, it's going to be 1. It always maps to whatever the first number is here. Next, we'll identify what our initial condition is, what our v at t naught is, where this t naught is this t naught. So in other words, we're going to start off by asking, what is v of 0? And then last, we're going to find the answer to the question that we were originally asked, which is, what is that voltage for any variable t in that time region? And we can write down the modified version of this that we got from last slide, which is that the way we'll actually evaluate that is by integrating over that smaller area and then add our v of t naught to it, which is going to be the area to the left of t naught. So I'll write down the formula for that right over here. Okay, so let's begin with the first region. We want to find an equation that's valid for any time between 0 and 1 that will give us the area to the left of an arbitrary point in this region. So just to make it concrete again, we want to find the equation for this area for some t naught that exists between 0 and 1. And what is that area? So the answer, v of t and v of t for that region, we want to find the integral between t and t naught and t of I of tau. Now, if I of t is 3t squared, then I of tau has to be 3 tau squared, plus our initial condition, which we need to find. Now, this initial condition for the very beginning of the problem has to be given to you. And it was. We said up here it's 2. So in the very beginning, we bring that down here. So now this is just a simple calculus equation. Shouldn't be hard to solve. The integral of 3 tau squared with respect to tau would be, we can bring that 3 out. The integral of tau squared is 1/3 tau cubed, and we're going to evaluate that between tau is 0 and t, plus our initial condition. So that gives us tau cubed, evaluated between tau equals 0 and t, plus 2. And that gives us t cubed minus 0, which is just, we don't have to write, plus our initial condition. So this is our answer for what v is. This is what our answer is for this shaded blue area for t naught, as long as t naught is somewhere between 0 and 1. Now notice how different this is than what you probably did in calculus, where you ended up evaluating not to get a function, but a number. You wanted to find the actual area between 0 and 6, 0 and 1/2. But now you're going to end up with a function, because we don't know where you're going to end up. We don't know exactly the upper limit. We just want it to be valid for any upper limit that's true between 0 and 1. So let's continue it on the next line. The next line in this region between 1 and 3, our I of t is a straight line. So from 8th grade math, the equation for I of t, this straight line, it's clearly got a slope that's rise over run. Its rise is 1, its run is 2, right? It spans 2 units between here. And it's a negative slope. It's going down. And we can't say it's the line is equal to, I of t is equal to just negative 1/2 t in this region, because it has an x-intercept, it has a vertical intercept when t equals 3. So we're going to have to shift it by 3, and we're going to either add or subtract it by 3. We're going to either add or subtract 3, and the way to remember that is when we put in 3 for t, clearly our answer is 0, so that means we have to subtract. So that's just a quick review of, or that's an application of your 8th grade math of how to find the equation for a straight line. Our v of t naught is tricky. Now we need to find our v of 1, and we're not given that. We're only given the v of 0. But you can recognize that this is valid for anywhere between t equals 0 and just under 1. And by being just under, if you evaluate it at 0.99999 repeating decimal, that would be 1. So to find v of 1, use this value and plug in 1 for t. You'll get 3. So that's our initial condition. And now v of t in that region is equal to the integral between our initial time, which is 1, to t, of our current, which is minus 1/2. I'm going to just multiply it out. I'm going to use the distributive property, plus 3/2 dt. I should have used a dummy variable here. I should have called this tau. And then we're going to add to it our initial condition of 3. So once again, we've converted a hard engineering problem to a much easier math problem. And now just grind the crank out. If we integrate negative 1/2 t, you can see that's going to give us negative 1/4 tau squared. And that will be evaluated between 1 and t. And next we'll integrate 3 over 2 d tau, which will give us 3 over 2 tau, evaluated for tau equals 1 to t. And then finally plus 3. So that's a lot of algebra. Let's do it quickly. The first one becomes minus 1/4 t squared. And then from that, I think it might be easier just to evaluate it like this. Now, putting in 1 for tau squared gives us 1. Doing the same thing for the second gives us t minus 1. And doing the same thing for the third part is just plain old plus 3. So now we can use the distributive property to find out how much of t squared do we have. And the answer is minus 1/4 t squared. Okay, that's a good amount. How much t do we have? The only place it's giving us any t is from this thing. So that would be plus 3/2 t. And then everything else is going to give us constants. So let's see. This part is going to give us plus 1/4. This part is going to give us minus 3/2. And this last part is going to give us plus 3. So all this is equal to minus 1/4 t squared plus 3/2 t plus 1 3/4 plus 7/4. And that's the answer for the amount of area underneath this curve anywhere in this region when we start our integration all the way off at negative infinity. Doesn't seem like we left much room for our last region of integration, but that's going to be our simplest. For t greater than or equal to 3, I of t in that region is 0. It's flat. Our initial time is going to be 0. It's going to be 3. Our initial voltage will be this evaluated at 3. So that's going to be minus 9/4 plus 9/2 plus 7/4. And that abomination is equal to 4. And so our v of t, which is going to be equal to the integral between 3 and t of 0 d tau plus 4. Well, the integral of 0 is going to be 0, so it's just equal to 4. So those are our 3 answers, each with their region. And just to review where the numbers come from, this comes by evaluating this at the initial condition. Similarly, if you evaluate this at the initial condition, you get that. So now there has to be a better way to write our answer because this looks pretty messy. And the best way to write the answer is by summarizing it all and saying v of t is equal to t cubed plus 2 or minus 1/4 t squared plus 3/2t plus 7/4 or 4 for 0 is less than t is less than 1, for 1 is less than t is less than 3, or for t is greater than 3, and you want to have equality signs in there. Truly doesn't matter where you put the equalities. You could put the equalities everywhere if you wanted to, because what this is doing at 1 is the same as what this is doing at 1, and what this is doing at 3 is the same as what this is doing at 3. And once you've written those, then this is the answer to the problem.